Hello seniors, today we're going to see electronic assignment number 11, which is applications of geometric and arithmetic patterns. And basically what we're going to see during this class is how we can apply the concepts that we've learned about arithmetic and geometric sequences into real life situations, okay? So the objective for this class is only one: apply arithmetic and geometric sequences to solve problems. So let's start by looking at this investigation problem. It says, if a person deposits $1,000 in a savings account, which pays interest at a rate of 4% annually, and makes no other withdrawals or deposits, how much will be in the account after 10 years? Okay, so you see that this is a real thing, right? People usually do savings in the banks or loans or whatever, and these interest rates are applied using geometric or arithmetic sequences. So it says, when the interest is compounded annually, that means that it is paid once per year, the amount in the account at the end of each year will be 104% of the amount at the start of the year. That's if the interest rate is of 4%. That means multiply the previous amount by 1.04, right? If we write 104% as decimals, that's the same as saying 1.04. The amount in the account after 10 years would be this amount, right? 1,000, which is the initial, times the interest rate, which is 104%. That's because it increases 4% each year, to the power of 10, right? So because it's 10 years from now. So by the end of the 10th year, I should have $1,480.24. Okay, so this is an example of a geometric sequence. You see that we have the first term, which is the initial deposit. We have the common ratio, which is this number over here, 1.04, because it's 104% of the previous year. And we have the value of n, which is 10, right? 10 years after. Okay, so it says you can think of the amount of money in the account at the end of each year as a geometric sequence with U1 equal to 1,000 and R equals to 1.04. So if we look at it this way, U1, the first term, is 1,000. For the end of the first year, we would have 1,000 times 1.04. We would have $1,040. Then for the second year, the end of the second year, or the start of the third year, we would have the U2, which will be the previous number we got here, times the common ratio, which is 1.04, and so on, okay? So if we want to calculate, for example, the amount we will have after 10 years, if we use this logic, you would see that U1 corresponds to year 0, right? Which means the initial time, right? So if we want to calculate U10, not U10, the amount of money I will have after 10 years, I would have to calculate U11 instead, right? So this logic is a little bit confusing. I'm going to show you later on in an example how I prefer to do this in order to avoid confusion, okay? So if we want to calculate the amount of money after 10 years, I would have to calculate U11, which is what is calculated right here, right? So UN equals 1,000, the initial, times the common ratio to the power of 11 minus 1. That's if we use our formula. Remember, the formula for geometric is UN equals U1 times R to the power of n minus 1. This is a formula for the nth term. Okay, so if we do that, you see that we get the same value we got here, right? Then it says, now consider what happens when interest is compounded more than once each year. Okay, here it says, in questions like this, the term per annum is sometimes used rather than annually or once a year. Okay, so those are synonyms. Okay, so here's an interesting formula, which is not in the formula booklet, and it is widely used in financials. This is known as compound interest. So let's analyze this formula, what each of the terms represent. So A, here it says A is the amount of money in the account. It's like the future value I will have after some time. R is the interest rate, a percentage written as a decimal. In this case, for example, if you wanna write 4%, that's 0.04, and the rate that we use in this formula should always be a rate given in years, per annum. So it says the rate is generally given per year, 4% per annum. That's what the bank, for example, tells you. I'm gonna make you a loan with an interest rate of 4% per year. Okay, then we have N, which is the number of times per year that the interest is compounded. So this is a new concept. For example, when you make a loan from a bank, they might tell you it's a 4% interest per annum, but it is compounded twice a year. That means that the bank will charge for the loan, or will calculate the value of the loan that needs to be paid twice per year, okay? And that'll be 2% at the first semester of the year, and the remaining 2% at the end of the year, in order to totalize the 4% of the interest rate per year, okay? T is the number of years, and P is a principal. It's the initial amount of money that we deposit. So it says you can find the amount of money in the account using this formula over here, which I rewrote this using our simple notation, or the U that you are used to in order for you to understand this better. So A is the same as saying U, or UN. In this case, I'm not using N here because N is representing another thing in this formula, and rather I'm using T, which represents time, okay? So time would play the role of the position that we used to do, which we used to represent with N, okay? So UT equals UO, U0, which is the amount I put in the beginning, the initial amount of money, times 1 plus R over N, where R is the interest rate, N is the number of compounding periods, to the power of N times T, okay? Where T is the amount of years I want to deposit my money, for example. So here's a brief demonstration about where this formula comes from, which is the same as this formula. I don't want to waste too much time explaining this, but if you want to take a look at this, maybe you can pause the video in order to see how I demonstrated the formula. You can do that, okay? The formula was demonstrated by assuming an initial value of n equal 1. N equals 1 means this. If n equals 1, interest generated are calculated once per year. If n equals 2, for example, interest generated are calculated twice per year, every 6 months. If n equals 3, then it's 3 times a year, and so on. Okay? So the demonstration was done, the initial demonstration was done using n equals 1 for simplicity purposes. So we get this formula. And here I make the general formula, which is if n is different from 1. And here's an important explanation I wrote. Here it says the term r over n, which is the green one circled over here, is the rate by which your interest will be calculated each time. Example, if r is 0.04, that's 4%, and n equals 2, this means that your interest rate will be of 0.04 divided by 2, which is 0.02, calculated every twice per year. That means that after 6 months, I will charge 2% of my loan, and at the end of the year, I will be charged the remaining 2% of the loan. Then, this exponent over here, the term n times t is the number of times the interest is calculated. Example, if n equals 3, that is, the loan is charged 3 times per year, and t equals 2, that means that it will be, the loan goes for 2 years. It says, the interest generated will be calculated 3 times 2, 6 times. Why is that? Because over a period of 2 years, the interest was calculated 3 times per year. Okay, so 2 times 3 gives us 6 total amount of calculating the interest. Okay. Observation, t is always in years. When we talk about the variable t, we're always referring to years. Okay, so let's see the first financial application of this electronic assignment. It says, a person deposits $1,000 in an account which pays an interest of 4% APR. APR is annual percentage rate, compounded quarterly. Assuming that the person makes no additional withdrawals or deposits, how much will be in the account after 10 years? Okay, so first of all, this is a formula that I just brought from the theory up there. So we're gonna identify all the pieces of information. First of all, this deposit of $1,000 is P, right? So I'm gonna write P equals $100. Then, in an account which pays an interest of 4% annual percentage rate, right? The annual percentage rate is the R for our formula. So R equals 4%, which is the same as saying 0.04. Okay, then it says compounded quarterly. That means that I'm gonna be charged 4 times, or the deposit, the interest of the deposit will be calculated 4 times. Quarterly comes from 4. 4 times per year. That means that N is 4. Okay. Assuming that the person makes no additional withdrawal deposit, how much will be in the account after 10 years? The 10 years represents the value of t. So t equals 10. We could write it years. Okay, so once we have all of the information, I can already calculate A, which is what we're asked. How much will be in the account after 10 years? So by applying the formula, we would get A equals 1,000 times 1 plus 0.04 over n, which is 4, to the power of 4 times t, which is 10. If we calculate this using our calculator, we would get, let me see, 1,000 times 1 plus 0.04 over 4 to the power of 40. This is $1488. We could say $0.9 and leave it there. Okay, so how much money did I make in this 10 years? If I had $1,000 and now I have this amount of money, the money I made, my earning, would be the difference, right? Which would be $488.9, which is what this result minus 1,000. Okay, but we're not asked to find that, so I'm only going to erase this. But just for you to think about that. Okay, then another type of application is population growth. Let's see this example. The population of a small town increases by 2% per year. If the population at the start of 1980 was this, what is the predicted population at the start of 2020? Okay, so for population growth, we can think about this would be definitely a geometric sequence, right? Because we're talking about a rate of increasing numbers, right? So if I write the formula for the geometric sequence, remember it's UN equals U1 times R to the power of n minus 1. This is our original formula, right? When we talk about population growth, well, first of all, let's try to identify our pieces of information. First of all, we have a common ratio or a rate of increasing numbers, which will be our value of R, right? Now, Pay very close attention here. Normally, people would make the mistake and say that R is directly 2%, which equals 0.02. But this is a huge mistake. Why? Because if we say so, we're saying, and we apply this into our formula, we're going to get a decreasing geometric sequence because this value is less than 1, right? But that's wrong because the population should actually be increasing throughout time, okay? That's the normal trend. So this is a mistake. The common ratio is not 2% for this formula, but it rather is, how much do you think? It should be 102%, right? Because it increases by 2% each year. So if this number was my 100% of the population in 1980, for the next year, it would be 102% greater. So this number plus the 2%, okay? That's the idea that's why the common ratio is 102 and not 2%. So this is 1.02 is the actual common ratio, okay? Another way to view this is if you don't wanna see the common ratio as 102%, you could rewrite this formula by saying the following: UN equals U1 times 1 plus R to the power of n minus 1. This is also valid. And in this case, you would write R as 0.02%, because when adding it to 1, which is 100%, you will be getting 1.02, which is 102%, which is the same number we have over here, okay? That's another way of viewing this problem. Maybe if you want to use that formula, maybe it's easier for you, okay? Now that I showed you that, I'm gonna do it with that formula. So if I erase this, I would tell you that we can rewrite this as UN equals U1 times 1 plus R to the power of n minus 1, okay? So here, if I'm using this formula, the value of R is 2%, which is 0.02, if I use this formula, okay? So U1, the initial population, is 12,500, right? Now, the other common misconception is, if I want to find the population at the start of 2020, how many years have passed since 1980? I would have to do the subtraction there. 2020 minus 1980 equals 40 years, okay? So the value of n, if you're gonna use this formula, the value of n should actually be 41, okay? In order to have to the power of 40, which is what we need. So if we calculate U41, we're gonna have the population for 2020, which would be U1 is this number times 1 plus 0.02 to the power of 41 minus 1, which is U40, which is 40, right? So U41, the population for 2020 would be times 1 plus 0.02 to the power of 40. This gives us 27600.5. And we could just leave it as 2661 because we're talking about people, right? So I'm just gonna round this up here. And that'll be the population for the year 2020, okay? Another way of thinking about this, which might be easier for you because it's more logical, is if you think about this formula as the following: UN equals U0 instead of U1 times 1 plus R to the power of n. And in this case, we're just leaving it as n because if we modify the formula, remember, here we have u1, so it's minus 1. If we have u0, this would be minus 0, which is the same as saying n, right? So we could just leave it like that. So here, if we want to calculate the population after 40 years, we could directly write here u40, okay? So u0 is the initial population, which is 12500, 1 plus 0.02 to the power of 40 directly, okay? So this formula may be a little bit less confusing for you, and you'll get the same result, 27601. This is another way of thinking about the problem, which I think it'll be easier for you. Okay, now let's see this problem. It says a plastic cup is 12 centimeters high. When 5 cups are stacked together, the stack is 15 centimeters high. How high would a stack of 20 cups stand, and how many cups would it take to make a stack at least 1 meter high? Okay, so let's try to solve this problem without using the concepts of sequences, first of all. So we're gonna try solving this without knowing sequences. So we know that the first cup, this one over here, measures 12 centimeters, right? 12 centimeters. Then, when 5 cups are stacked together, the stack is 15 centimeters high. Let's see if I can identify 5. This is first, second, third, fourth, fifth. So this height is of 15 centimeters, right? So, without knowing sequences, I could say that that there's a common difference here, right? When we stack the, let me zoom in here. When I stack the cups, I get a little height from each, right? D, and so on. Okay, how can we calculate that difference in height? If 15 centimeters is the height for all the 5 cups, this equals what? 12 centimeters, which is the initial height of the first cup, plus how many times did I add the common difference? If I stack up 5 cups, I get 4 times that little difference. So I can call this 4D, right? So I can calculate how much height each of the stacked cups is adding by solving this. So this would be 3 equals 4D. So D is 3/4. That means that each cup is adding a height of 3/4, which is the same as saying 0.75 centimeters. Okay? So, to answer part A, it says, how high would a stack of 20 cups stand? We could write this. You see that now that we've seen the problem without the concept of sequences, we can start relating this now to sequences, and you'll see that this formula over here is what type of sequence? This is an arithmetic sequence. Remember arithmetic sequence? I'm going to write it here. Arithmetic sequence. The formula for the arithmetic sequence is un equals u1 plus n minus 1 times the common difference. And you see that we did exactly that reasoning in this problem. U1 is cup number 1, right? Which is 12 centimeters high. And we did n minus 1, which is exactly this 4 over here. If we have 5 cups, the value of n would be 5. So 5 minus 1 gives us 4. And the common difference is that little height that each of the cups is adding, right? Which in this case is 0.75 or 3/4 centimeters. So this is 0.75 centimeters. So Now, if we apply the concept of arithmetic sequences to solve part A, we would say that U20 is what we need to find because we want to know how high will 20 cups stand. This will be equal to U1, which is 12, plus N is 20 minus 1 times the common difference, which is 3/4 or 0.75. So U20 gives us, if we calculate this is 12 plus 19 times 3/4, which give us 26.25 centimeters. So this is how high 20 cups would be, right? Then for part B, how many cups would it take to make a stack at least 1 meter high? 1 meter, if we pass this to centimeters, this is the same as saying 1 meter is 100 centimeters. So if we want to have a height of at least 100 centimeters, we could use this 100 as our UN, right? So we could say 100 equals U1, which is 12, plus N, we don't know the value of N, we want to know the number of cups, times the common difference, which is 3/4. So then we would solve for N and get the value. This is 88 equals 3/4 of N minus 1. If I take this dividing to the other side, 88 divided by 3/4 gives us an ugly number. This is, I'm going to do it here. This gives us 352/3. And this equals N minus 1. So the value of N gives us, if I do this plus 1, this is 118.3, and this continues 3. So N, in order to have a height greater than 1 meter, we should round this number up, right? We cannot have a decimal number of cups, so we need to round this up in order to have a height greater than 1 meter. If we round it down to 118, we would get a height less than 1 meter. So I need 119 cups. You see how we can apply sequences to solve these types of problems too. Okay, next problem. It says an arithmetic sequence is defined by UN equals 12n minus 7, and a geometric sequence is defined by Vn equals 0.3 times 1.2 to the power of n minus 1. Find the least number of terms such that Vn is greater than Un. Okay, this is actually not a real life application, but it's interesting for me to show you how you can use your calculator to solve this very quickly. So our condition is to find the least number of terms such that Vn is greater than Un. So Vn must be greater than Un. In order to do that, we can rewrite this as 0.3 times 1.2 to the power of n minus 1, and this should be greater than Un, which is 12n minus 7. In order to solve this quickly, one way to do so is to directly graph both functions in our calculator and see where they intersect. Okay, so let's do this using our calculator. I'm gonna draw this. Let me show you here. So this is a calculator. We need to go to menu graph, that's menu 5. And I'm going to erase this. And we're going to plug in both equations. The first equation, remember, it's the Vn, which is 0.3 times 1.2 to the power of x minus 1. That's our first function. And the second one is 12x minus 7. Once we have the two functions written, we're going to draw this. Press F6, and you see the red one is the arithmetic sequence. It's a line graph. And the blue one is the geometric sequence. It's an exponential graph. So what we want to know is when this blue function exceeds or passes the red one. So we're not able to see that here. We need to adjust the window. So we're going to go to Shift V Windows, and maybe we can plug in max. Let me see. We can put this from 0 to 50, for example. Scale 1, it's fine. And the y, we could go from -5, for example. It should actually be, we're going to put it 0. And x should also be 0, because we cannot talk about negative numbers of n. And the maximum value, we could write as, I don't know, 600. You can try this by plugging in any values. It could be scale 10 to make it a little bit smaller. Then exit and draw again, F6. And now you see that the blue function exceeds or passes the red function after this intersection point over here, which we can calculate. How do we calculate this? Shift G solve, and then we find the intersection point, which is F5. If we calculate the intersection point, you see that we get an intersection point down here, but this number corresponds is 0.6, which is not valid, right? Because remember, the value of n should always be an integer number. And for x equals 1, the red function is already up. And for x equals 0, the blue function is greater than the red one, but the value of x cannot be 0. The value of x should be 1 or greater, okay? So let's go to the second point, and we get this result. X equals 41.6. 41.6. That is the intersection point. So if we go back to the problem, I'm going to write the steps here using GDC. And we're going to, using the GDC, we're going to sketch both graphs and find the intersection point. So by doing that, we get that the value of n, which is x in our calculator, gives us 41.6. But remember, the value of n can never be a decimal number, so we need to round this up, right? We need to round it up because that will be the first value for which Vn would be greater than Un. Okay, so n equals 42 is the least number of terms such that Vn is greater than Un. Okay, so I hope you understood how to use a calculator in this case. Now let's see number 3. I think we have 2 more. Yes. It says a series has a formula, and we have the formula for the series. Find S1, S2, S3, and for part B, find U1, U2, and U3. I think we could do both together in this case. So this is the formula for the sum. Well, we are already given the formula, so we're going to use this formula. So to find S1, that is the sum of the first one term of the sequence, this would be S1 equals 2 to the power of 1 plus 2 minus 4. We just replace the value of n by 1. So this gives us 2 to the power of 3 is 8. 8 minus 4 is 4. Okay, so S1 is the sum of the first one term of the sequence, right? So S1 is the same as U1 because we're adding only one number, which is 4 in this case. So we already found S1 and U1 at the same time. So this is actually A and B together. So we have S1 and we have U1. There. Then S of 2, the sum of the first two terms of the sequence. This would be 2 to the power of 2 plus 2 minus 4, if we replace the value of n by 2. So this gives us, this is 4, 16, 16 minus 4 is, no, 2 to the power of 4. Yes, 2 to the power of 4 is 16 minus 4, 12. So S of 2 is the same as saying, this is the answer already for S of 2. S of 2 is the same as saying u1 plus u2, right? So S of 2 is 4, we already found u1, plus u2. So now we're going to find the value of u2. We know that S of 2 is 12, so u2 gives us 12 minus 4, which is 8. So this is the second term of this sequence. So we already found S2 and U2. Finally, for S3 and U3, we're going to do the same. S of 3, we're going to apply this formula. Is 2 to the power of 3 plus 2, 2 to the power of 3 plus 2 minus 4. If we solve this, this gives us 2 to the power of 5 is 32, 32 minus 4 is 28. Okay, so S of 3 is the same as saying u1 plus u2 plus u3. We already have u1, we already have u2, so we can solve this. 28 equals u1, which is 4, plus u2, which is 8, plus u3, which we don't know. So this is 28 minus 12. 28 minus 12 is 16. So u3 equals 16. Okay, so we have S of 3 and U3. So we finished part A and part B. Finally, for part C, I'm going to do part C over here. So part C says, write an expression for un. You see that? We have u1 is 4. I'm going to write them here. u1 is 4, u2 is 8, and u3 is 16. Do you notice a pattern here in order to be able to write un, which will be the general term of this equation? What I see here is that 4 is the same as saying 2 to the power of 2, 8 is 2 to the power of 3, and 16 is 2 to the power of 4. So maybe un should be, let's see, this is 1 degree more than the position. So this should be 2 to the power of n plus 1. This should be the answer for un. So un, the general expression would be 2 to the power of n plus 1. And you can try this if you want. If you calculate, for example, u3 using this formula, this should be 2 to the power of 3 plus 1, which is 2 to the power of 4. And 2 to the power of 4 is actually 16. So yes, this is correct. So this is the general term for this sequence over here, which it does not necessarily need to be arithmetic or geometric. It could be any type of sequence. You just need to notice the pattern. Finally, last exercise. 2 species of spiders inhabit a remote island. The population of species A is this, and is increasing at a rate of this per month. The population of species B is 50,000 and is decreasing at a rate of 175 spiders each month. When will the population of species A be greater than the population of species B? Okay, so if you notice, there are 2 different types of sequences here. The first type of sequence is a geometric sequence because it's increasing at a common ratio of 1.5% per each month, while the second sequence is an arithmetic sequence because it's decreasing at a constant number each month. It's always 175 spiders less each month. So that's a common difference between the terms. So I'm going to write here the information. Species A is a geometric sequence while species B corresponds to a arithmetic sequence. There you go. So for species A, we have an initial population which would be U1 equals 12,000, and a common ratio. If we're going to use the formula, I'm going to write both formulas before. Remember the formula, UN equals U1 times R to the power of n minus 1, and in this case it's UN equals U1 plus n minus 1 times D. So if we're going to use this formula, the common ratio should actually be 1 plus 1.25, because it's, no, not like this. It's 100%, I'm going to write it like this, 100% plus 1.25%, which give us 101.25%, right? And if we write this in decimal by dividing it by 100, this gives us, this would be 101.25 divided by 100, which is 1.0125. This is the value of R in the first case. So the equation would be UN equals 12,000 times 1.0125 to the power of n minus 1. That's our equation for species A. Now, if we go to species B, we know that U1 is 50,000 in this case. 50,000. Then we know that D, the common difference, is, it says decreasing at a rate of 175 spiders each month. So the number of D should be negative 175. We're decreasing 175 spiders each month. So our general equation would be UN equals 50,000 times, plus n minus 1 times negative 175. So there you have the two different equations, and we want to know when will the population of species A be greater than the population of species B. So basically what we want to do is set up this equation to be greater than this equation over here, which is the same thing we did in the previous problem. So I'm going to write this here, 12,000 times 1.0125 should be greater than 50,000 plus n minus 1 times negative 175. And once again, we could solve this quickly by using our calculator, which is what I'm going to show you right now. Okay, so if we go back to the calculator, this is the previous problem, so I'm gonna erase this, delete, and we're gonna plug in the new equation. The first one is 12,000 times 1.0125 to the power of x minus 1, and the second equation is 50,000 plus parentheses x minus 1 times, get the parentheses, negative 175. There you go. So once we have both equations written, we draw this by pressing F6, and you see that, well, we don't see anything because the zoom is not correct. Let's try by doing zoom auto. There you have. But we still cannot see the intersection clearly. So we're gonna change the window a little bit. we're going to put as x min, we could put 0, x max, we could put 100, scale 10, y mean, we could just leave this as maybe 0, and maximum would be 50,000. So we'll go back. Oh, the scale is not correct there. Okay, we can see the intersection already. So you see that the red function, which is the arithmetic sequence, which is decreasing, is greater than the blue one for all the previous interval, right? And after this point, the blue function is greater than the red one, okay? So we want to find that intersection point by clicking on Shift G solve and intersect, right? F5. So there we have. In the month, 87.04, the blue function, the geometric sequence would be greater. So if we go back to the problem now. If we go back to the problem, we already have the answer. The answer, using GDC, we would get that the value of n is 87.04, but we need to round this up, right? So to have it as an integer number, so n equals 88 months is the answer for this problem. At the month number 88, the geometric sequence, species A, would be greater than the arithmetic sequence, which is species B. Okay, so I hope you understood this, seniors. If you have any questions, do not hesitate to ask it in the Google class.